Dear students, in last class we designed Butterworth digital IIR high pass filter using bilinear transformation. Today we will take up a problem on design of Butterworth digital IIR low pass filter using Impulse Invariant Transformation. Example: design a Butterworth digital IIR low pass filter using Impulse Invariant Transformation by taking t equal to 1 second to satisfy the following specifications. Gain in normal value is greater than or equal to 0.707 and less than or equal to 1.0 for a passband having bandwidth of 0 to 0.3 pi and gain in normal value is less than or equal to 0.2 for stop band between 0.75 pi to pi. Solution. First we will write specifications of digital IIR low pass filter. Passband edge digital frequency omega p is equal to 0.3 pi radians per sample. Stop band edge digital frequency omega s equal to 0.75 pi radians per sample. Gain in normal value at passband edge is equal to 0.707 and gain in normal value at stop band edge is 0.2. 0.707 may be denoted by AP and 0.2 may be denoted by AS. To design digital low pass filter, first we have to design an analog low pass filter using impulse invariant transformation. So we need to convert digital frequencies into analog frequencies using impulse invariant transformation frequency relationships, but the gains are to be kept same. Passband edge digital frequency omega p is equal to digital passband frequency omega p by sampling time t, that is equal to 0.3 pi by 1, that is equal to 0.9425 radians per second. Similarly, stopband edge analog frequency omega s is equal to digital stopband frequency omega s by t, that is equal to 0.75 pi by 1, which is equal to 2.3562 radians per second. So what we have done here, we have converted the digital frequencies into corresponding analog frequencies using the relationships between analog frequency and digital frequency in IIT. Next, we have to calculate order of the filter. Remember here, stopband edge gain and passband edge gain will remain same. That is, AS is equal to 0.2 and AP is equal to 0.707 only. They won't change. We have N1 equal to log of 1 by A square minus 1 upon 1 by AP square minus 1 whole divided by log of omega s by omega p, that is equal to we have N1 equal to half into log of 1 upon AS square minus 1 by 1 by AP square minus 1 whole divided by log of omega s by omega p, that is equal to half into log of 1 upon 0.2 square minus 1 by 1 by 0.707 square minus 1 log of 2.3562 by 0.9425. On simplification we get N1 equal to 1.7339. Order of the filter cannot be in decimal form, therefore we have to convert this into a positive integer. So rounding off 1.7339 to the next highest integer, we get n equal to 2. Now order of the filter is 2. Using order of the filter, now we have to write for normalized transfer function of analog filter. Normalized transfer function that is h of Sn of Butterworth low pass filter. For even n, h of Sn is product of 1 upon Sn square plus bk into Sn plus 1 for k equal to 1 to n by 2, where bk is equal to 2 times sine of 2k minus 1 into pi by 2n. Here k is equal to 1 to n by 2, that is k equal to 1 to 2 by 2, that means 1 only. First we will calculate b1 value. b1 is equal to 2 into sine of 2 into 1 minus 1 bracket complete into pi divided by 2 into 2, because n is equal to 2, that is order of the filter is 2. Two into sine of pi by 4 that is 2 into 0.707, which is equal to 1.4142. Therefore, normalized transfer function h of Sn is equal to 1 upon Sn square plus 1.4142 Sn plus 1. From this normalized transfer function h of Sn, we have to obtain unnormalized transfer function, that is h of S of Butterworth low pass filter by substituting for Sn equal to S upon omega c. For that, what we need then? We need cutoff frequency omega c. So first we will calculate cutoff frequency omega c, and then we will obtain h of S. Cutoff frequency omega c is equal to omega S upon 1 by A square minus 1 raised to 1 by 2n, that is equal to 2.3562 by 1 by 0.2 whole square minus 1 raised to 1 by 4. This 4 is nothing but 2 into 2, because order of the filter is 2. So when we simplify, we get the cutoff frequency as 1.0645 radians per second. This is analog frequency, so unit will be radians per second. Now we will write for unnormalized transfer function h of S. Unnormalized transfer function that is h of S of Butterworth low pass filter. H of S equal to H of Sn at Sn equal to S by omega c. That is, H of S is equal to 1 upon S by omega c square plus S upon omega c into 1.4142 plus 1, or we can write it as omega c square divided by S square plus S into omega c into 1.4142 plus omega c square, that is equal to 1.0645 square by S square plus S into 1.0645 into 1.4142 plus 1.0645 squared. Simplifying, we get 1.1332 divided by s square plus 1.5054s plus 1.1332. So what is this? This is unnormalized transfer function of Butterworth low pass filter. Now we have to convert h of s into h of z using impulse invariant transformation. To convert analog transfer function to digital transfer function, the above equation can be modified as follows. Here we will complete a square in denominator and write it in the form of s plus a whole square plus b square. H of s is equal to 1.1332 In one of the previous class, I have taught you how to complete the square, and also you have learnt that in your 10th standard, right? I hope you will be able to do that. So by using all your mathematical knowledge, we can write this as now s plus 0.7527 whole square plus 0.5666. Now we have to make use of standard relationship between h of s and h of z, that is b upon s plus a whole square plus b square. Is transformed to e raised to minus at into sine of bt into z raised to minus 1 upon 1 minus 2 into e raised to minus at into cos of bt into z raised to minus 1 plus e raised to minus 2at into z raised to minus 2. Now you can observe here from this relationship and the available h of s that 0.5666 is not the square of 1.1332. So you have to modify h of s to write it in b upon s plus a square plus b square form. That is, we will write h of s as 1.1332 into 0.7527 divided by s plus 0.7527 whole square plus 0.7527 whole square, because 0.7527 whole square is 0.5666. And now for us, this is extra term, so we'll divide 1.1332 by 0.7527. That means our h of s, that is here, is in unchanged form. Simplifying, we get h of s equal to 1.5055 into 0.7527 divided by s plus 0.7527 whole square plus 0.7527 whole square. Using standard relationship, between h of s and h of z, the transfer function of digital IIR low pass filter h of z will now become 1.5055. This is constant, we have to keep it as it is. E raised to minus 0.7527. T value is 1, so into 1 into sine of 0.7527 into 1 into z raised to minus 1 whole divided by 1 minus e raised to minus 0.7527 into 1 into cos of 0.7527 into 1 into z raised to minus 1 plus e raised to minus 2 into 0.7527 into 1 into z raised to minus 2. On simplification, we get 1.5055 into 0.322 z raised to minus 1 whole divided by 1 minus here I have missed 2, so just I will enter 2 here, right? And if I do that, then I would get 0.6877 into z raised to minus 1 plus 0.22 19 z raised to minus 2. Multiplying 1.5055 with 0.3220, we get 0.4848 z raised to minus 1, whereas the denominator remains the same, that is 1 minus 0.6877 into z raised to minus 1 plus 0.2219 z raised to minus 2. So this is the transfer function of digital low pass filter to satisfy the specifications. Dear students, as in case of first problem, I ask you to calculate the frequency response and plot the graph. Today I will stop the class here. Thank you.